Hey, I know how much you guys love videos, so here we go. We're into rotational dynamics. So we already did dynamics last semester. That was the whole second quarter, the old famous stuff. Old Newton's laws of motion. Well, guys, it's a return of the FMA, but only Greek style, meaning we're doing things in a circle. So force is what causes an acceleration if it's an unbalanced force. Well, what causes an angular acceleration is an unbalanced torque. So if you have balanced torques, there's no angular acceleration. That's like if you're just balancing things. Same thing here. If you don't have an unbalanced force, there's no acceleration. And how big that acceleration is depends on the mass or the inertia of the object. Well, when you spin, that inertia is a lot more complicated than just knowing the mass of the object, because it's not just the amount of mass, it's where the mass is located and how much it is and how is it spinning. So that's the moment of inertia of the object spinning, which is the same as this is the inertia of the object going in a straight line. It's a little more complicated when you spin. It's more than just the amount of mass. It's where it's located and how is it spinning. So that's the torque or force-like thing. If it's unbalanced torque, it causes the acceleration. And of course, that's your angular acceleration. So let's get rolling here. So the moment of inertia or rotational inertia depends on two things. Well, three things. One is the mass. Two is the radius of that mass. And the third thing is how is that thing spinning. So to find that moment of inertia, we're summing up all those masses where they are in terms of each other compared to how it's spinning. So the units are going to be a kilogram meters squared. Okay? That's the unit for the moment of inertia. So it only affects things that are spinning or relative to spinning. It doesn't have to be spinning, but it's in reference to the inertia or resistance to a change in spin. So if things are at rest, they want to stay at rest. So this is the resistance to going into a circle. Or if it's already spinning, stopping the spin. This is the resistance to a change. This is how you measure the inertia of a change in rotational motion. Okay, so it depends on the mass and its distribution and how it spins because of that distribution. Okay, and of course, the further that mass is from the point of rotation, the greater the inertia. All right, for example, so all of these masses it's going to make easy math because they're all the same distance from the point of rotation in the middle. Since they're all the same distance away, all you do is sum up all the masses. Mass 1 plus mass 2, mass 3. You add up the total mass, and the R is all the same. So that's really easy. So as long as all the mass is at the same distance away, it doesn't matter if it's a planet at that distance or if it's a ring. Since the mass is all at the same distance, it's a relatively easy thing to find the moment of inertia or the rotational inertia of an object. So this is not going to be that hard either, but we've got different masses and how they're distributed. Hey, they're blowing some answers over here already. But anyway, so how do you find the total moment of inertia about the x-axis? Well, that means it spins across here. So what we're going to do is, let's get out my writing utensil there. So if I want to find the moment of inertia, the total inertia about the x, well, what I'm going to do is do the m r squared. Now, since we're going about the x-axis here, there actually is no radius for the 3 because they're right on the axis there. So the only thing that matters for rotational inertia are the things that are at a distance off of that axis, the 2's. Now, these are all 0.6 meters, so if you do your little trig thingy or your 45, you divide by the square root of 2, you're going to find that every one of these lines is a 0.42 meters-ish. There's a little more, but the 2 sig figs, they're only showing 1. It's about 0.42. So really all I have to do, the R is a 0.42 for all of those masses, for each one, for both of those, And since they're at the same distance, rather than doing 2 of these, when I sum all this stuff up, I just add the 2 masses together, so it's 4. So 4 times 0.42 squared is, boom, about 0.72. Now if we go across the y-axis over here, let me change up my colors over here. Let me change up to a little blue. So if we go around the y-axis over here, now these things that are 2 kilograms essentially have almost no radius. There's a teeny bit, but not much, not appreciable. So we're only worried about the 3s over here. So now the total moment of inertia of about the y-axis, I'm summing up all the masses, what's 3? And since they're the same distance, I don't have to do them separately. Since they're the same distance away, I can just add them together. That's a 6 kilograms. And once again, they're all at the same distance from the point of rotation on the y-axis here, the 0.42 away. So times 0.42 meters, and I square that. That's going to be that answer, 1.08. Now the z-axis is another story. The z-axis is, let's go with the black. That's coming right out at your face right here. So if you imagine this coming right at your face, that's positive z. Into the screen there is your negative z. So it's spinning around one way or the other. It could spin that way, it could spin that way. It doesn't matter which way it spins. It's the resistance to a change in that motion. Well, the good news is they're all the same distance from that point of rotation. So as we sum up all those masses, the r is going to be the same, 0.42 meters. And since they're all the same distance, it's actually all I have to do is add up all the masses. That's 6 and a 4, that's 10. It's just 10 times the 0.42. And that's how you get your 1.8. So the moral of the story is it depends on not just the amount of mass, it's where the mass is located and how it spins. If it spins around the x-axis, that's rotational inertia. It's harder to spin around the y because you've got 50% more mass, and even harder to go around the c because now you got around the z-axis, because now all the masses are spinning around that. So it's not just the amount of mass and how far they are away from the point of rotation, it's how the thing is spinning. Okay? That's why it gets a little complicated there. Alright, so let's get rid of the pen and let's erase all link on that slide. Alright, let's go to our next dealio. So these shapes are now this one's the easy one. That's the I equals mr. All the mass, since it's rotating about the center, is located at the same distance. So it's a pretty easy equation. That's the mr squared stuff. Not as easy as this one because it's not all on the outside. Some of it's on the inside, some of it's halfway out. So you have to average where all that mass is. And when you average where all that mass is, that's where you get the 1/2 mr squared. Now when you start talking about a sphere, it gets even more complicated. Because a sphere is, well, here's the thing. So not all the mass is at that r distance away. Some of the mass is at pretty much 0, and some is half the r, and some less than half the r, some more than half the r. So because you have mass all over the place, you have to use a little trig. So this is beyond the scope of a college physics, but not a university physics where you do the calculus stuff. In the calculus version of this class, you might have to actually solve this and find out how would you derive how the mass is distributed, where you do an integral of summing up all the masses at some distance, and you end up with the 2/5 mr squared. And if it's hollow, it's greater moment of inertia than it is for the solid because all the mass on average is further out than that. But that's still less inertia than this because all the mass isn't all located on the very outside. But it's more inertia than this, but of course of the 4 objects, this has the least. So this is the easiest to start in motion, but it's also the easiest to stop. This is the hardest object to start in motion, but it's also the hardest to stop once it gets in motion because it's got more inertia. Now, sometimes we just have a rod that spins. If this rod were to spin on the axis like this, like rolling down the ramp like some of you guys did on race day, that's actually a solid cylinder. That's this formula. But now if you take that same cylinder or disc and you rotate it around the middle like this, it works out a little differently. We're not using the R anymore. Because we're not using the R, using the L, the math kind of works out to be a 1/12. They're just trying to make your math work easier for you. Using the whole length like so to find the moment of inertia. And just as this swinging around one end. Okay, so we're not rolling down the ramp. We're just swinging a rod, a round rod in a circle like that. It's a 1/3 ml, that being the length to find the moment of inertia. So those are some common shapes that would make your problem solving a little bit easier when finding the angular acceleration of things, or later on the velocity of things when you have a change in energy from a potential to kinetic or kinetic to potential, by knowing what the moment of inertia is, or even when we get into the momentum. Those are important things to know. So you don't really have to memorize these things. Maybe that one, the mr squared, for all the mass being at the same spot. But you don't have to memorize all these different equations. They'll be generally given to you in the problems, or you'll have a way to look that stuff up. All right, let's keep on rolling. We might get done in time. So these are some examples. Your cylindrical shell, like the bicycle rim, all the mass is near the outside, mostly. There are spokes. Solid cylinder, filled can of pumpkin, because it's pretty solid throughout. Baton, it's spinning around the middle. Baseball bat, it's spinning around one end. That's why it's the 1/3. The mass of the bat times the length. This is the entire length, not the radius like these. It's the entire length. Basketball, that's the radius of the basketball. It's hollow in the middle. And of course, like your bowling ball, solid in the middle, the 2/5. That'd be a lower moment of inertia. Okay, let's see if we can get a problem done in a couple minutes. I have to work fast. I don't know if I can do that or not. So, moment of inertia of this thing. Well, guys, this is a solid disc. So if you want to back up the truck a little bit, a solid disc, that's this thing here, 1/2 mr squared. That's this thing here, filled can of pumpkin rolling. It's not as delicious as a can of pumpkin, but it's the same thing. It's a solid disc. So if we want to find the moment of inertia of that thing, what we're going to have to do is, let's go with blue on that. It's just going to be a 1/2 mr squared. So all we have to do is 1/2 the mass, so it's going to be 1/2 the 5 kilograms times the radius, 0.6. Don't forget to square that thing, and zoom. There's going to be what your answer is. And if I click this, it might even pop up. Oh, they all popped up. Let me back up a little bit. So 2.5, which is a, oops, I'm not even on. So 2.5 times 0.6 squared equals, that's going to be about a 0.9 kilogram meter squared for that. We're going to need that in a moment. All right, how do you find the tension on that rope? Well, the tension on, oh, for the tension, we don't have to find it. It's right there. The tension is 10. What's the angular acceleration? Well, guys, that's what we're going to use here. This torque equals the moment of inertia times the angular acceleration. So since we know the torque, we're going to solve for the angular acceleration there, meaning that's going to be the torque divided by the moment of inertia there. And the moment of inertia we found is the 0.9 kilogram meter squared. The torque is the 10 newtons times the radius of 0.6. So 10 times 0.6 is 6. So if I take 6 divided by 0.9, boom, that's a 6.666666, or 6.67 radians per second squared. Guys, we're going to get timed out on this thing, but I can do the acceleration really fast, because look at this. All that is the angular acceleration times the radius of that thing. The angular acceleration is 6.666666 radians per second squared times the radius of that thing, 0.6. So all I do is take that times 0.6 times 0.6, and then I'm going to get a 4. Well, that is easy. 4 meters per second squared. Almost finished the whole thing, but I got to stop because that's what the YouTube says.